Hey, how you doing? Mr. H here. We are into day 2 of exponential growth and decay, but now we're actually going to get into the applications, hey, when am I ever going to use that part? So a couple of just real basic things to look at here at the beginning. First one is going to be when a real life quantity increases by a fixed percent each year or day or month or whatever it happens to be. We've got these two models. We have one for growth and one for decay. And the only difference between them is growth gets plus, it's adding, it makes sense. And decay or something decreasing gets minus. And we call that 1 plus r or that 1 minus r our growth or our decay factor. It's letting us know by what percentage something is increasing or decreasing. Everything else, r is our rate is a decimal. A is what we start with. It may be bacteria, it may be money, it could be all sorts of things. And then T is going to be our time in years. So when we look at this first one, let's just kind of jump in. A scientist estimates that a specimen begins with 730 bacteria. Okay, that's my A value. If this specimen grows by 35%, now be careful here. R isn't 35. When we do 35%, you're doing 35 out of 100, or 35 divided by 100, which is 0.35, which we can also get by just moving the decimal place 2 places to the left. Okay, every minute, write an equation that represents the bacteria's growth. Okay, so growth, we're going to be following this one. So the A, Y, that really doesn't matter. That's a capital A anyway, so it's not our little one. So what we start with, 1 plus our rate. And then most of the time, we're not going to be told what that T value is. So you can put T here, you can put X, you can put anything you want, but that's the format for this, and that's it, okay? If it's the equation, we're done. But there's another question. How many minutes will pass before the bacteria reaches a population of 9,000? Use your table. Okay, so let's pull this up. So we're going to go to y equals, and we're going to type our equation in. Or we're going to get it where it already can do it. There we go. Oops, not minus. Plus 0.35. We're going to use x since we don't have t available to us. If we put it in as a letter, it wouldn't look at it as a variable. So what we're going to do is we're going to hit second graph because we want the table. How many minutes will pass before the bacteria reaches a population of 9,000? So I start here at 0. I have 730, and I start scrolling. Now you're like, well, it never says 9,000. It says like 8,053, and then it says 10,872. What do I do? Okay. When we're not looking for an exact value, which we're not right now, there's a way to get it exact, but that's another time, another story. We're just going to look over here at our X values and say, hey, this is our time. This is our bacteria. So the time would be somewhere between 8 to 9 minutes, okay? We're not worried about minutes and seconds right now. We could, again, figure that out, but that's a little further down the road. Okay, that's it. Let's see here. Another one, you buy a car for $36,000. A value. The value Y of the car decreases, goes down by 14% each year. Okay, write a decay model for the value of the car. Y equals the value we're starting with. Since it decreases, that's 1 minus my rate. And again, Tx doesn't matter what I put up there, but that's my model. Okay, find the value after 3 years. Now this time I'm going to show you a little trick. Just in case you want a different way of going about this, I'm going to give you an option here. So here I get my 36,000 minus 0.14 is the X. So I can still pull my chart, find the value after 3 years, go down to 3. Now do hover over this, and it's a little detail thing again. I'm not going to tell you you're wrong if you put 22,898, but if you actually put this over this, you notice there's a couple of cents involved, and I'm going to write those. But 22 $8.98.02. Now, let's say you still, for some reason, haven't downloaded this. I'm really not quite sure why at this point. You also, just in a regular calculator, could type in 36,000, 1 minus 0.14. But what you would do instead is you want to know the value after 3 years. That's time. You put in the 3, you get the exact same answer. Okay? We like using the y equals because it gives us flexibility. If there were several questions, I can answer them all without having to retype it in every time. But if you're just looking for one answer, this is an option for you. So graph the model on your calculator and see, if we move Hardy's head out of the way here, we might be able to see. When the car will have a value of 15,000. Okay, let's go back to the y equals. We don't really need the graph. We just need the chart because we remember now we're looking to see above 15,000, below 15,000. So somewhere in here, we went below 15,000, between 5 and 6 years. Okay, keep it simple. That's the key today. All right, let's see, we got any other fun stuff here? Oh, we do. Okay. The growth of an antique table's value after 1975, move myself again here, is represented by the equation 325, 1.03 to the t. It is there. What was the value of the table in 1975? Okay, that is just going to be my a value. Why? In 1975, this is what's called the base year. And when it's the base year, your t equals 0. So if you think about that for a minute, if you have 325 times 1.03 to the 0 power, what's anything to the 0 power equal? 1. So this whole thing here equals 1, and 325 times 1 is 325. So if you're ever asked the value of something in the base year, it's just whatever your a value is. What is the rate of growth? Now, be careful here. A growth factor and a rate of growth are two different things, because we talked about the growth factor would be this whole thing. The rate of growth is always 1 plus whatever that percentage is. So you're like, so is the rate of growth 0.03? No. Okay, what does 0.03 equal as a percentage? If we want the decimal back to the percentage, we move 2 places to the right, or we multiply by 100. So my rate of growth would be 3%. Okay, if this would have been a number less than 1. So let's just say, for example, it was 325.96. Okay, this would have a rate of decay. You're like, why is it decay? Because it's less than 1. It's getting smaller, of 4%. You're like, now how'd you get 4%? How far below 100% or 1 is 0.96? So if it's below 1, it's decay. If it's above 1, it's growth. This is why we put all this stuff down on paper here. So then when we go back later and are doing something, we're like, oh, we don't get all going, I don't know what he's talking about. Now you do, because this also may be written as 1 minus 0.04 is another way I could write this. Or that 1.03, okay, that could be written as 1 plus 0.03 to the x. So there's so many different ways in math that we can say and write things that when we do something like this in a lesson, it's really important that we kind of lock in on what could something look like. Okay. But again, as always, if you have questions, shoot them my way. We can work them out live as well. So finally, we got a couple more formulas left. Compound interest. Holy cow, look at all those variables. P is our initial principal, how much money we started with. R is the annual interest rate as a decimal. We've already talked about those. N is the number of times compounded in 1 year. So here's what that means. So if you say something is compounded, let's say daily, N would be 365. Okay. If we said monthly, N would be 12 because 12 months happen in a year. Okay. Quarterly. There's 4 quarters in a year. Okay. 4 3-month periods. So that's all that we're saying. Whenever we see the word compounded, we're going to have to figure out what this N value is. And then T is the number of years. So here we go. All right. We're going to start with letter A here. You deposited $1,000 in an account. Okay, that's my P. That pays 8% annual interest. And if you're ever not sure on one of those, again, 8 divided by 100. The decimal will be right there, and then I can use it. Now, N, annually. Annually means it happens once a year. So my N value would be 1. And then my little exponent up here is N times T. Now, I do and I don't know. It says find the balance after 1 year. So in this case, my T is going to be 1. So we're just going to put the 1 in here. And you can use the table. Now, you don't need to here because we're only looking for one thing. 1,000. 1 plus 0.08 divided by 1 to the 1 times 1 power. And I would have $1,080 at the end of that year. Now, does it make a difference what that N value is? We talked about quarterly up above being 4. Everything else is the same. Same principal, same rate. The only difference is in these 2 spots where these N's are, we're going to do 4 now instead of 1. Let's see what happens. Well, okay, we made a little more. Might have a little extra money for that extra McDouble or something here this time. Okay, so quarterly changed it a little. I got more interest more often, but it's not like life-changing. Okay, and then daily is 365. Now you'd be like, okay, Hardy, this is going to have to make a bigger difference, right? Because, I mean, we're taking something basically to the 365th power. I mean, this number's going to be huge, right? Hardy, why aren't you answering? Why are you just typing? Because I think you might be a little bit surprised at what we see. You're like, I can't even get an extra drink off the dollar menu. It's like not even $1 more. Are you serious? This is what, though, sometimes banks and businesses are going to use to try and get you to do something. To, oh, it's compounded daily. You know, that it doesn't make any difference. Well, I mean, it makes a little difference, but not that much difference. How many years will it take for an account to double its value if it collects 4.5% interest compounded monthly? Okay. So we're like 0.045 is our rate. Compounded monthly, okay, N equals 12. Hardy, they didn't tell me how much money I'm starting with. They didn't give me the p-value. Like I've got the 1 and the 0.05 and the 12 and the 12. Now, I don't know what that number is. I don't know how many years. That's my X, but they didn't tell me the principal. What do I do? Okay. If you are given no principal, if you are given no starting value, make 1 up. Okay. The answer you get at the same end will be the same, whether you put in 100, 1,000, 1,000,000, whatever. Okay. Mathematically, it's going to grow at the same percentage. It's just the amount you're doing. So normally I just use 1,000. If you want to use 1,000,000, if you want to use $1, I'm telling you, it'll do the same thing. And we're going to use our table here because we don't know a value of time. So we need a little help here. So okay, and don't forget that x up in your exponent up here, because otherwise this kind of just gets trashed. So I pull my chart. I start with 1,000. How long is it going to take for my account to double? So in my instance, double would be, when does y get to be greater than 2,000? If you did 1,000,000, it would be greater than 2,000,000. If you did 100, it'd be greater than 200. So I'm looking to see when this gets bigger than 2,000. And once it does, oh, there it went. Lower than 2,000, higher than 2,000. So somewhere here between 15 to 16 years. And if you don't believe me that it doesn't matter what principal number I use, try it with a different one and see if you get the same thing. All right, one last formula to throw in here. However, interest can be compounded continuously. Doesn't that sound awesome? Like nonstop money. The formula is A equals PE. Okay. E, to get E on your calculator, is second and natural log. Okay, it's down the left-hand side here. So you have to hit second with this first, but then there's a little e to the x. Because E is a number. Okay, it's like 2.717. I don't remember anything past that. So, $1,000, 8% for 1 year. Here we go. So, $1,000. E never changes. E is always going to be there. And then our rate times our time. This one we don't need the chart. 1,000 second natural log. There's my E. Notice it automatically goes up to an exponent for me. 0.08 times 1 year. 1,083.29. Always go to that nearest cent. When you're talking about money, always go to the nearest cent unless you're specifically told. You can go to the nearest dollar or something else like that. Okay, 800 at 7% for 3 years. Principal, E, again, continuously is always E, 0.07 times 3. 800 second ln, 0.07 times 3. 986.94. Okay, but continuously is the only time we use this formula. If we're given any other values, we're just using the regular compound interest formula. How long will it take for an account balance to triple? 3 times as much if it collects 5% continuously. Did they give me a number at the beginning? Does that mean we can't do the problem? Make your account balance at the beginning anything you want. I'm an old fogey. I just stick with 1,000. So 1,000, there's my expression. E, there's my rate. We don't know what this is, but here's what I do know. I do know, and I should have put that up here too. When I was doubling, this needed to equal 2,000. Now here, since it's tripling, this needs to equal 3,000. So when does y get bigger than 3,000 using this formula? We can only stick that part in the calculator. Second ln, 0.05x. Pull my chart. And again, the goal, 3,000. When I see 3,000, I can stop going. Oh, saw 3,000, there it is. So it's between these two, really close to this one, but nonetheless between them, 21 to 22 years. Okay, that is going to do it for this one. There is a practice that goes with this. I am going to quickly try and find said practice. We'll see how quickly the quickly part of this is. almost there. I see stuff that looks familiar. I thought I saw stuff that looks familiar. Oh, we're close. There it is. Applications of exponentials. It is the same. It is in your packet, page 2, as you can see at the top here. Again, it talks about tripling, doubling, and some things like that, but it goes along right with the notes this time. There are no surprises. Okay, so try these out. Try out the problems online. And as always, if you have questions, fire them my way. We'll see you next time.